In this video, we will cover fully connected neural network architecture. This deals with how to arrange the different number of hidden layers and neurons. Neural networks are usually represented without the learnable parameters. In this example, the hidden layer has 4 neurons. The output layer has 1 neuron. We can make multi-class predictions using neural networks. We just add more neurons to the output layer. The process can be thought of as just replacing the output layer with a softmax function. Here, the output layer has 3 neurons for 3 classes. For a given input, we obtain an output for each neuron. We choose the class according to the index of the neuron that has the largest value. In this case, neuron 2 has the largest value, so the output of our model is 2. We can use the following diagram. We have 5 neurons in the output layer, 1 for each class dog, cat, and so on. We can add hidden layers. Here we have 2 hidden layers. If we have more than 1 hidden layer, the neural network is called a deep neural network. More neurons or more layers may lead to overfitting. The output or activation of each layer is the same dimension as the number of neurons. This layer has 3 neurons. The output or activation has 3 dimensions. Each neuron is like a linear classifier. Therefore, each neuron must have the same number of inputs as the previous layer. In this case, the previous layer has 3 neurons, so this neuron has 3 inputs. Let's see how the following neural network makes a prediction in the following layers. Consider the following input vector with 4 dimensions. Each neuron in the first layer has 4 inputs. As there are 3 neurons, the activation has a dimension of 3. Each neuron in the next layer has an input dimension of 3. As there is 2 neurons in the second layer, the output activation has a dimension of 2. One way to select a fully connected neural network architecture is to use the validation data. Consider the following network architecture A, B, and C. We select the architecture with the best performance on the validation data, in this case, C. It turns out that deep networks work better, but are hard to train. If you recall, to perform gradient descent to obtain our learning parameters, we have to calculate the gradient. But the deeper the network, the smaller the gradient gets. This is called the vanishing gradient. As a result, it's harder to train the deeper layers of the network. One of the main drawbacks with using the sigmoid activation function is the vanishing gradient. One activation function is the rectified linear unit function, or ReLU function for short. The value of the ReLU function is 0 when its input is less than 0. ReLU is only used in the hidden layers. If the input z is larger than 0, the input of the function will equal its output. If the input z equals 5, the output equals 5. If the input z equals 10, the output equals 10. Networks have layers that help with training. We will skip the details, but some methods like dropout prevent overfitting. Batch normalization to help with training. Skip connections allow you to train deeper networks by connecting deeper layers during training. The hidden layers of neural networks replace the kernels in SVMs. We can use the raw image or features like HOG. Training neural networks is more of an art than a science, so we will use the lab to try out different methods generally. Neural networks are trained in a similar manner to logistic regression and softmax. The loss or cost surface is complicated, making training difficult. In the lab, we will explore more advanced variants of gradient descent. Other advanced methods to prevent overfitting. That's it. Check out the lab for more.